Hello everyone, my name is Jamil Vito and today I will be discussing mathematics in nature and the arts. Mathematical concepts and influences can be seen in both nature and human creation such as art. Art and other creative forms have been highly influenced by the relationship between mathematical concepts and aesthetics, especially in postmodern art and historical art, where artists such as Vincent van Gogh, Leonardo da Vinci, and Claude Monet used mathematical concepts in their artworks. The Starry Night, Mona Lisa, and Water Lilies, respectively. In addition, seeing patterns in nature has also led many to believe that such patterns seen in nature are evidence of a divine creation. Now let's first talk about the Fibonacci sequence and the golden ratio. The Fibonacci sequence are numbers that follow a certain pattern, named after Leonardo of Pisa, aka Fibonacci, who first discovered the pattern while investigating how fast rabbits could breed under ideal circumstances. The first few numbers in the sequence are 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, so on and so forth. And in order to get the next number in the Fibonacci sequence, you only have to add the current number to the previous number. So to continue the sequence, 89 plus 55 would be 144, making 144 the next number in the sequence. We can also get the Fibonacci number through the use of Binet's formula. Now, it's time for some interesting fun facts. Number 1. Did you know that the sum and differences of Fibonacci numbers are also Fibonacci numbers? Number 2. The Fibonacci sequence can also be seen in nature through things such as seeds in sunflowers and spirals in pine cones, for example. It just shows that Fibonacci sequences can be seen in everything, even in our daily lives. Number 3. The ratios of Fibonacci numbers converge to a particular number which is called the golden ratio. Now, what is the golden ratio? Well, the golden ratio is an irrational number which is also known as a golden number or divine proportion. It shows a mathematical relationship between two quantities, often denoted as the Greek letter phi, and is approximately equal to 1.61803398875 or simply 1.618. The golden ratio can be defined in two ways, algebraically and geometrically. Algebraically, the ratio of a line segment cut into two parts of different lengths such that the ratio of the whole segment to the larger segment is equal to the ratio of the larger segment to the smaller segment. Geometrically, the ratio of the side of a regular pentagon to the side of a regular decagon. The golden ratio is often found in nature, art, and architecture. Some of the examples include in nature, as mentioned earlier, the spirals in a pine cone and the seeds in a sunflower. In art, as mentioned as well earlier, the paintings of Leonardo da Vinci and other notable artists. And in architecture, the proportions of the facade in the Notre Dame Cathedral. The golden ratio is a fascinating and mysterious number that has been studied for centuries. It is found in many different areas of human endeavor, and it continues to be a source of inspiration for artists, scientists, and mathematicians alike. Next, we will discuss patterns and isometries. Well, if you really think about it, math is a study of patterns. Patterns that may be numerical, logical, or geometric. It is to be taken note of that the pattern has symmetry if there is an isometry of the plane that preserves the pattern. Moreover, in patterns and isometries, we would also be tackling transformation, which is a process that shifts points of the plane to possibly new locations in the plane. In this presentation, we would be tackling transformations such as translation, reflection, rotation, and dilation, as well as isometry of the plane, which is the mapping that preserves distance and therefore shape. Translation, reflection, rotation, and glide reflection. Now, let us discuss each of these very quick but clearly. Translation or slide moves shape in a given direction by sliding it up, down, sideways, or diagonally. Reflection or flip is like how it is named. It is simply a mirror image of flipping the shape horizontally. Rotation or turn has a point about which the rotation is made and an angle that says how far the rotation is. Dilation is a transformation in which the size of an object changes. Glide reflection is a combination of reflection and translation. Now moving into isometries, let us first define what they are. Rooted from the Greek word isos, meaning equal, and metron, meaning measure, isometries are transformations which leave the dimensions of an object and its image unchanged. It is inflexible. Symmetric patterns. The types of symmetric patterns are the following: rosette patterns, frieze patterns, and wallpaper patterns. To easily understand these, rosette patterns are a finite group of isometries which contain just rotations and reflections. There are two types of rosette patterns. One is cyclic, which does not have a rotational symmetry, and dihedral, which has reflectional symmetry. Frieze patterns are an infinitely long strip implanted into a design given by a repeating motif. It has translational symmetry in one direction, and wallpaper patterns, on the other hand, are similar to frieze patterns, only that wallpaper patterns copy their pattern by translation in the second direction and must at least have two rows of each on at least 2 units long. Tessellation is a repeating pattern of figures that completely covers a plane without gaps or overlaps. Tessellations can be created with the use of translation, rotation, and reflections. Moreover, these are two types of tessellations: regular tessellation, in which are made out of congruent regular polygons, and semi-regular tessellations, which uses a variety of regular polygons. Last but not least, we are going to discuss fractals. So what are fractals? Well, fractals are jagged repeated forms that are characterized by their infinite detail and self-similarity, which means that they appear similar at all scales of magnification. This property gives fractals their unique and intricate beauty. Properties of fractals. First, fractals are infinitely complex, meaning that they can be zoomed in on indefinitely and still reveal new detail. 2. Fractals are self-similar, meaning that they could contain smaller copies of themselves at all scales of magnification. And 3. Fractals have a fractional dimension, which is measured of how much space they fill. Fractional dimensions are always greater than one of the ordinary objects like lines, circles, and spheres, but they can be less than one for fractals. Now, let's delve into the history and the discovery of fractals. First person on our list is Georg Cantor, who is a German mathematician who is considered to be the father of the set theory and has made great significant contributions to the field of mathematics. He developed the theory of transfinite numbers, the concept of cardinal numbers, and the proof that the set of real numbers is uncountably larger than the set of natural numbers. Next is Hedge von Kusch, who is known for his contribution to fractals, more specifically for the Koch snowflake, which is one of the most famous fractals. Next is Gaston Julia, who is a French mathematician who created the Julia set, which began with him questioning what would happen when you take a simple equation and you iterate it through a feedback link, then plug it into the same formula. Fast forward, the Julia set was born. Next, we have Mandelbrot, who is the mathematician who created the Mandelbrot set, which is known to be the emblem of fractal geometry. He used a computer to run the equation millions of times, then turned the numbers from his Julia sets to the points in a graph. And lastly, Nathan Cohen created or invented the fractal antenna, which is widely used in wireless devices and cell phones. His idea was to make an antenna that would be more compact but provide better frequency. And with utilizing fractals, he was able to create the fractal antenna. There are other famous fractals other than the Koch snowflake and the others mentioned in this video. There are others such as the dragon curve, Sierpinski's triangle, Menger's sponge, and many more. In addition, fractals are often applied to day-to-day life even without you knowing. Fractals can be seen in arts, finance, computer graphics, and medical imaging, just to name a few. Well, that is all for this video. Thank you so much for taking the time to watch this video until the very end. I hope that you were able to get new knowledge and be able to use the things that you've learned in this video in day to day life and in your math subjects. Thank you so much.